questions from the homework in chapter 4? Yeah. 15. Oh. Let's see, this is page 168. So they're talking about the data back, table 4.1. Sample 1. Let's see, here we go. Yeah. Oh yeah, this stuff here. The lying and not lying, right? Like on the meet the parents. If 4 of them are selected without replacement, find the probability that the polygraph indicates that the subject lied. So what I would do on that, let me try to recreate this correctly. Number 15. Let's see. Positive. Test. Negative. Test. Not lie. Lied. 15. 2. 14. So what's the probability that a good place to start when you're picking more than one person is just do one person first. Figure out what that is by itself. What's the probability that one person had a test result come out positive?
57.
Yeah, so positive test result, there's a total of 57.
Yes.
And then there's a total of 98 people. Cool, right? So the bottom is always the total number. It could be any of the 98 people. And we have 57 that got positive test results. That's on the top. Beautiful. So when I take 4 of these people, I'm hoping you guys start to realize, I like my little hangman game. I got 1, 2, 3, 4 people. I just got to fill in the probabilities for each, right? So the first guy, nothing's happened yet.
1 over 98.
We just figured out the probability,
57.
right? So 57 out of 98. Now I put that person in the next room over. So what happens now?
56.
I love it.
7.
I like it. There's only 97 people now. And there's only 56 that had positive test results. Because I just picked one person that had a positive test result and put them somewhere else. So now there's one less of each.
55.
And so forth. You start to see the pattern as you go down. Right, 55.
Bless you. 96.
And you just got to multiply that out.
Yes.
Right? So in your calculator, you can just put 57 divided by 98 times 56 divided by 97, so forth, right? Don't freak that you have to be able to input fractions. Fractions are division problems. So your calculator is fine with that. What is this really right here? This is something I want to this is one last little thing I want to firm up from chapter 4. What is that thing?
At least
What the hell is that? Why did it change from what it was for one person? Why did it change?
You didn't replace.
I didn't replace, so something happened, right?
Yes, you removed it. You
So-
kept it gone.
The only time a probability for something can really change is if something occurs, some new information happens or something changes in the environment. And sure enough, so this is really the probability that I get a positive result given that I already took somebody out that had a positive result, right? Okay. So that's the one last thing I need to change. In fact, that's why this guy changed. Why did this change? Why didn't this guy change? Why is he the same as if it was one person? Because so far, at this point, nothing's happened. I haven't changed anything. I haven't taken somebody yet. The probability I get this person, 57 out of 98, throw them out the room, right? The next one changes. Why? Because it's given that something happened. So that really is one of those conditional probabilities. And this is even more conditional. Given that 2 of these things happened. Given that 3 of these things happened. There you go. That's why it keeps changing down the road. Right? So what's really sucky, and this is just the truth, is that if you try to apply the formula on different types of problems, it makes it more difficult. People always, if I look at this by itself, and I just ask you what's the probability of somebody negative result and lied. Do I need a formula for that, really? Like a true formula where I calculate things? No. I mean, what would the answer be? Negative result and they lied.
9.
9 out of
98.
98, right? But everybody gets too focused on and is multiply. We're gonna no. You don't. There's nothing to multiply there, really. I mean, I just have to look it up. I've got the count. I could just count what I need. So sometimes when you try to use the formulas we talk about too often, they make it more difficult. And this kind of setup and really is just the intersection, right? Here's the negative result. Here's the lie. 9 of them are in both. Cool. And that's what goes on top. Because the last little thing I want to talk about that I really didn't put up here yet is weight. Who can remind me what's the formula for this? And what's that symbol there mean? I love it. What was the formula for that? It's like one of the last things we did last time. What definitely goes on the bottom?
Given that.
Yeah, the B, the given, right? So P of B, peanut and butter. And what goes on the top? Run jelly. Yeah, exactly. The only way, if I know B happened, the only way it could also be A is if it's in A and B. Right? So if I know I got a club, the only way it can be a king is if it's at one king that's a club. Right? So it's got to be A and B. Now, to kind of complete this, I want a formula for A and B directly. We have a formula for A or B, right? A plus B minus A and B. I want a formula for A and B directly. Can't I solve this for probability of A and B? It's a little algebra now. There's very little algebra in stats. This is one place where it shows up. How do I get this by itself? Multiply by this. So probability of A and B equals probability of B, get in there, times probability of A given B. Now what I want you to realize is that's exactly what this is, isn't it? What was this? These two would be the probability of the first guy's positive result and the second guy's positive result, right? So sure enough, to get that, I have to multiply the first guy times the second guy given the first guy. That's what that says. That's what that formula says. How often are we going to use that directly? Well, on these kind of problems. But do I even think of it as that equation? No, I think of it as just changing the numbers as I move along. But that really is that equation that we're using, right? So it's weird to hear a math person say this. But in probability especially, the formulas very often get in our way, to tell you honestly. But I want you to realize that is what we're doing here. We keep multiplying by the conditional things, and that's what it says to do. Multiply by the conditional, multiply by the conditional.
So, in the quiz, if we don't put the formula, does it matter? If
No.
we just do it like this.
Especially if I give you a problem like this. You should be able to get most of the probabilities just by looking at it, right?
I have a question for you.
Oh, and real quick, let me see. The mistake people make is they'll take, like if I wanted the probability negative result and lied, what's the probability of negative result by itself?
32 plus 9.
41.
Yeah, 41 out of 98. What's the probability of lied?
What, 57?
Well, lied would be
57.
51.
50.
And if you multiply these together, you will not get this. Right? So that's a mistake people make. And that's why, just like OR, can you just always add to get the ORs? No, you have to subtract sometimes too. You have to not count too much. Don't count something twice. To get an AND, can you just always multiply these? No. Because you have to multiply by the given. You'd actually have to do, so we can keep you guys with me here. If I wanted to use a formula, this formula here, to get the probability of a negative result and lie, I'd have to do probability negative result times probability of lied given negative result. So I'd have to actually calculate what the hell that was first. Do I really want to do that when an and is just look at the freaking intersection in the first place? Of course not, right? So when I have, the funny thing about probabilities, if I have the counts, I use those. I make the probabilities quick. I just look at the counts. When I don't have the counts, I use the formulas, because that's all I got. Throw stuff into the formulas then, right? Most of the time you're going to have the counts to work with. Okay, cool. Maybe. But the bad part is I had somebody ask me something earlier today. And kind of sucks because in English, and has several meanings. And we kind of went over this when I first introduced and. If I say I want you and you and you to come, then I'm going to add you guys and there's 3 people coming with me, right? But and does not mean add. In English, it could also mean, well, I need somebody who's knows computers really well, and they've worked at Microsoft, and they make over $400 million a year. And, then my pool of people gets smaller and smaller and smaller, right? And sure enough, probabilities are all between what 2 numbers? Probabilities have to be between
0 and 1.
And when you multiply numbers that are truly fractions, don't they become smaller?
Mm-hmm.
1/2 times 1/2 is 1/4. So and makes things smaller. Multiplying fractions make things smaller. That's why and is basically multiply. Or is basically add, like we said before. Cool. Okay. Maybe.
I'm kind of curious. Is for the or, how come in another math this is all like kind of union everything?
Oh, yeah.
Together?
Yeah, well, that's what or does, isn't it?
Mm-hmm, yeah.
So if you've taken some math where they talk about sets, where you have the symbol for or is like this. Have anybody ever seen that?
Yeah,
Symbol for
that's
or.
what I use.
Some probability books actually have that symbol in there. Here they just decided not to. It's the same thing. Or says you could be in this or that. I'll take everybody. That's why or is basically add, right? Add everybody here to everybody there. And don't count anybody twice, right? Whereas and says you got to be in this one and that one. So if I had, for example, this might be useful here. Let's say that A was 1, 2, 3, and B was 2, 4, 7. What's A and B?
2.
Beautiful, because it says and here means. Just like in English has double meaning, and probability has one meaning. It means it's got to be both. So the only thing that's both A and B is 2. So it gets smaller there, right? If I said A or B, good Lord, Jeff. Now it could be in A or B. What would that list look like?
The whole
1, 2,
thing.
3, 4, 7.
Yeah, don't write 2 twice. Right. Cool. Okay, maybe. I'm very hopeful. Okay. But it's really, if you haven't gotten into this homework yet, you just desperately need to, so you can see what the hell it could look like. Yeah.
Number 18.
Okay. I'm waiting for the alarm clock question. I don't know. Has anybody gotten to the
Oh
alarm
no,
clock
I did
question?
that already.
Was it all right?
It was.
Yeah, it was fun.
Good. All right. That's good to hear. This is what I normally expect to get questions about.
In what? 4, 4?
Oh, I forget where it is.
Here's 4, 4.
So number 18 and 4, 4? So 18, I think, refers down to the chart that's on the bottom of page 168. So this is about blood types. I don't know if I want to recopy that real quick here. See, O, A, B, A.
That's true.
So it's
35, 8, 2.
oh, sorry. It's all right. All of a sudden, I went the other way. And 18 says if 3 of the people from here, and thankfully they tell me there's 100 total people there. If 3 people selected, good Lord, Jeff, can you spell? Find the probability that they are all Group B in type RH, assuming that they're. So the first one says with replacement. And let me try to write this. Find the probability that they are all Group B and
RH negative.
RH negative. So all this. Well, what's one? So again, my suggestion, when they start picking more than one thing, you start identifying all the single probabilities by themselves, and then you can start multiplying whatever you need to from there, right? So what's probability that one person is B and RH negative?
2 out of 100.
Yeah, so probably B and RH negative by itself is 2 out of 100. So if I do it with replacement, what kicks ass about that? How many blank spots do I have?
3.
3. I like it. You guys start to see there's a method to my madness here. I mean, so I got 3 blank spots because I got 3 freaking people that I'm picking. If I do it with replacement, the probability the first one's got B and RH negative.
2 out of 100.
I put him back in the mix.
2 out of 100.
Put him back in the mix.
2 out of 100.
Right? So that's with replacement. The question might actually be in part B, where things get a little bit weird, but not really. So this would just be something. Good. So it'll be 8 out of 100, 100, 100.
1 million.
8 out of a million chance, which makes sense. To get 3 people when there's only 2 out of 100 in the first place, that's going to be really freaking difficult to do at random, right? It's easy if they have a big card with their son. I just picked them. No, this is randomly. What's the chances of that happening randomly? Very small. What about part B where it says without replacement? This is actually kind of a silly question. Can you pick 3 people
No.
that match the description when there are only 2 of them? Well, if you start to try to set it up, what would it look like? Here's my
2 out of
3.
100.
Yeah, there's my 3 spots. 2 out of 100. You throw them away.
1 out
1
of
out of
99.
199.
0 out of
And then,
Zero.
and the math just stares you in the face. The math is saying, dude, it's 0. There's no way. Right? So you could actually do this with no work at all. If you just say real quick, I can't. There's only 2 in the first place. 0%. The math will back you up. Right? Yeah.
Can you do 4, 5, number 3? I'm not really. I mean, I don't know if my thinking would be right. Can I just say what I thought it was?
Sure, yeah.
Okay. I think that it's not correct because giving that the guy had a heart surgery, had a pacemaker, chances are his probability of survival will be a lot higher. But it's
I like it.
I-
So the mistake people make when they're, and this is the same problem we had with the Democrat Republican. So I appreciate when people are explaining to me that there are more parties and so forth, but we talked about in class, the problem is saying basically there are 2 parties. The third party gets votes sometimes, but it doesn't look like they'll ever get elected, right? So there's Democrat, Republican that's going to be in the White House. Just because there's 2 doesn't mean there's a 50-50 chance, right? There's definitely, depending on what's going on, there's more chance for this or that. So for somebody asking the doctor, what's the chances I'm going to survive? And the doc says, 50-50, you know. That's my little brother used to always tell me. And I always tell him that I give this example. He said, Jeff, you teach that probability stuff, right? I'm like, yeah. He says, you know, it's going to happen or it ain't. So leave those kids alone, man. It's 50-50. Everything's 50-50. I said, James, never become a freaking doctor. If I'm going in there and you're putting you're putting me out and I'm saying, Doc, what's my chances? Oh, 50-50. I'm like, no, it's just tonsillitis, man. We're 50-50. It should be 98% chance. Either going to die or not going to die. There you go. Right? So in this case, yes, exactly. There are other factors that doctors got to take into consideration. It's not just 50-50. They're not equally likely.
Right.
I can only do 1 out of how many there are if they're all equally likely. I like it. Cool. Is that good? Yeah.
A question pertaining to 18. So if I want to find out the sample space, would it be 100 or just 8 possibilities?
The sample space, I could pick. What kind of person can I pick? I could pick an RH positive O, an RH positive A. Yes, so there would be 8 possibilities, right?
So that's my sample space.
That's your sample space.
What is 100 then? It's just
100 is just the sample size, right? So remember we had that problem with the seeds, the flower seeds? If I said, what could happen? You pick 1 seed out, what could happen? You wouldn't say I could pick a red or a red or a red. I'm like, you already said freaking red. I don't care that there's 7 red seeds. You're going to say, what could happen? I could get a red or a white. You're not gonna, I don't care how many there are of each. Those are the things that could happen. How many there are of each factors into the probabilities. If there's more red, then red's a higher probability. Cool. But when you just tell me what's going to happen, what could happen, I don't care how many there are. Just tell me what could happen. What are the possible outcomes? Cool. Okay. Yeah.
Number 4 on 4.
Oh, there's a couple little things like this, little technical details. And I think I addressed this last time when I had the left-handed problem we did, where it was like L, R, R. Remember we were doing that towards the end of class? If my population is large relative to my sample, and there's a specific guideline that says if your sample is less than 5% of your population, you don't have to do this crazy thing here, where you change it each time, right? You could just say, if I'm taking 3 people, it'd be, in this 88% chance, it'd be 0.88 times 0.88 times 0.88. I don't have to figure out, like we did last time with 310 million people in the U.S. Do I really have to do over 310 million, over 309,999,900? No, thank God, no, because our sample's small relative to our population. They're not going to change that much. That's what the 5% guideline is. So, number 3, they selected 1,068, and their population was 477,000 something. So what percentage of the population was the sample? The sample's 1,068, whatever the hell it is, and the population is 477.
938.
938. Those are the samples. That's the size, and the population size. What percentage of the population was my sample then? How do you calculate that?
0.22
And how do you get that?
divided.
Yeah, divide it. So it'll be 1,068. So whatever the hell that is, right? And I'm pretty sure that's going to be below 5%, right? So you actually get 0.22%. So like 0.0022. Okay. So that's definitely 22%, which is less than 5%. Check. You can treat them as independent then. You don't have to change them each time you do it. Whereas when I only had 100 people, even that I could treat as independent, tell you honestly here, because picking 3 people out of 100, that's 3%. So that's less than 5%. I could treat that as independent.
The doctors are dependent.
Because, yeah.
No, the back of the book. So if you read the whole thing, it should say they're dependent, but you can treat them as independent, right? 4. Oh, well, there, yeah. Yes, the 5% guideline applies.
Yeah.
It's no more than 5%. And the calculations with dependent events would be too much work, right? So let me do a specific example, concrete example. Let's say I've got 4,000 people, and I picked 2. And let's say that 3,000 of them are Mormon. Not sure where they came from at all. So I'm somewhere where I just happen to be surrounded by a large percentage of Mormons. So if I pick 2 of them, what's the probability that one of them is Mormon? Let's just start with just one of them. Yeah, 3,000 out of 4,000, 75%, right? 3 out of 4. Now for 2 of them then, I'll have 2 blank spots. What's probably that both of them would be Mormon then? If you do it technically by the book, if you do it like this would be 3,000 over 4,000 times what? Yeah, 1 less Mormon, 1 less person. Now somebody help me out. What is 29.99 divided by 39.99? Can you help me out just on that specific one? What is that?
7.5.
Yeah, is that really far away from 75%? So what the 5% guideline says, since I'm taking 2 out of 4,000, that is less than 5% of my population, right? I don't have to do this crazy shit. I could just say, I've got 2 people. What's probably first one's Mormon, 75%. Second one, let's assume they're independent because it's just a small sample. It's not going to change that much anyway. You guys just saw that. If you do divide this, it's 0.749. That's freaking 75%. Leave me alone, right? That's what that means. Thank God, because can you imagine if I had 80,000 people and I want to pick 10 of them, and you want to set up each one of these? No, thank you, right? I'd rather figure out the percentage and just raise that to the 10th power. Multiply it 10 times. Much quicker. And completely legal because it really doesn't change that much. The probabilities don't change that much. Okay.
So you would just multiply this and that's it.
Yeah. So 75% and 75%.
56%.
56%. And if you do 3,000 or 4,000 times this over this, you get basically that. I mean, they're the same.
But
So
how
that's
do you-
why that guideline exists.
How can you tell if they're independent or dependent?
No. What's it say? If the sample you picked is less than 5% of the population. Right? Very specific. So if you have 4,000 people and you only pick 2, that's less than 5%.
And so it's dependent?
Are these, if I pick 2 people, if I pick one and put them next to me and pick another one, are they independent or dependent? They would definitely be dependent because I've changed it, right? What this rule says is even though they're dependent, you can see that right here, they changed, didn't it? The probability changed. It says you can treat them as if they're independent because it's easier to do. And because the number doesn't change that much. Cool. Okay. So that's what that rule is all about. That rule saves our ass so many times because normally our population is pretty damn big. So I want to be able to do calculations very quickly. Okay. So any other questions from? Yeah.
So they're talking about 6 and 9, whether they're independent or dependent. Seems like it depends on circumstances.
Yeah, it's really kind of difficult to find something that's truly independent. Let me give you an easy one from this real quick, and then we'll look at. Well, let me see, what is 6 all about? Oh, 6 is actually not too terrible if you think about it. I think the problem people get is they think that, well, it all depends on if the car is dead. But that's actually why they're dependent. If you find first that your car radio works, doesn't that affect the probability your headlights will work? If your car radio didn't work, if it didn't turn on, isn't there a better chance your headlights might not turn on because maybe your whole car's dead? So does one happening affect the probability of the other one? Yes, that's why they're dependent. Cool. Whereas if somebody over here, their calculator dies, does that affect the probability that the person back there, their calculator is going to die? Not really, no. So you could argue maybe there's a big rainstorm like there was and both calculators went, no, screw that. But they're basically independent. That should not affect that, right? But if my mom was a doctor, does that affect me becoming a doctor? What do you think? Of course, that might be influenced, right? I might say, well, if she was a doctor, I kind of got into that and I want to be a doctor. Okay. So
I guess where I'm confused, like with the car one, it's like, well, what about if the bulbs are out in the headlights? Like, I guess I'm thinking of circumstances.
So
They were-
affecting the chances of the other one does not mean one definitely means the other one's going to happen, right?
Okay.
But doesn't it make it, the chances change? Just like I love the example, and I don't know if you guys like this at all or not, but I love the example of a person getting off the motorcycle because, yes, women do ride motorcycles, but the probability that's a dude, if I see somebody get off a motorcycle, is higher than it would have been if it was just somebody I saw coming towards me. Or somebody I can't see, I don't know if it's a man or woman. Oh, they just got off a motorcycle, that's probably a dude, right? Does it mean it's definitely a dude? No, that's the whole point here. It's all probabilities. We can't say for sure, which is why a lot of people hate statistics. But like I said earlier in this class, stats is one of the most honest branches of mathematics. It says, I really don't freaking know, right? It just says, I can give you what I think, give you a feeling about it, but that's about it. That doesn't mean we throw it all out, because it definitely is useful. So like number 9, what do you think about this? Finding that your television works, finding that your refrigerator works. It's really the same idea. If your television's not turning on,
Chances are.
there's a good chance that maybe your power's out. Now, does that mean your television might itself have just died? That's one possibility. But if it doesn't turn on, that increases the chances that the fridge won't turn on. Maybe because that would happen if the whole power was out, right?
So they're dependent.
They are definitely dependent. Cool. But let me see which one. How about this? Finding that your calculator works, finding that your computer works. So if I take my calculator out and I'm like, oh, it works. Oh, good. That'll work now too.
They're independent.
They are independent. I love it. Cool. Okay.
But I do have one though, because I kind of had a hard time with this one. The 12, randomly selecting a consumer who owns a computer, randomly selecting a consumer who uses the internet.
So if you select somebody who owns a computer,
Oh, yeah.
does that affect the chances that that person uses the internet?
Yeah.
Go the other way. If you select somebody who said they don't have a computer at home, does that affect the chances that they use the internet? Does that affect the chances that they use the internet? Yes.
Okay.
Don't say, well, they could use the one at the school. No, I'm talking about the chances. Doesn't the chance that they use the internet go down if they don't have their own computer, right? Of course it does. Okay. They could still use it, I agree with you, but the chances that they use it have gone down at least a little bit. Okay, cool. Yeah.
24.
Okay, and this will be the last question. We got to get into new stuff. 24. Oh, beautiful. This is perfect. This is the kind of one I've been waiting for. Page in 4:4, right? 24. This is page 169. Riverhead, New York. 9 different crime victims listened to voice recordings of 5 different men. All 9 victims identify the same voice as that of the criminal. If the voice identifications were made by random guesses, find the probability that all 9 victims picked the same guy. So people get, this is a very confusing problem when you first read through it. But this is the probability that we use all the time. For example, DNA evidence. Right? There is a probability that if your DNA matches that at the crime scene, that it doesn't mean you were there. But it's a very, very small probability. So that's going to be, if your matches, you're going to jail. I'm sorry. Right? It's really hard to argue, well, there's a 0.00007% chance my client wasn't there. Screw that. We've got other stuff too, so that pretty much says he was there. This one's got one little thing that's a little weird to it. I'm going to try to explain it when we hit it. But what's probably that one person would pick somebody out of those? How many people are they picking from? Each of these 9 people.
5.
They're picking from 5 people. What's probably that one person would randomly pick the right guy?
1 out of 5.
I love it. Remember, whenever you get these 9, there's 7 people, pick 3 people, whatever, you want to first do 1 by itself. Right? So 1 by itself, there's a 1/5 chance. That's a musical interlude. I like it. So how many blank spots am I going to have? How many hangman spots?
9.
9. Cool. Okay, so 9 spots. One of them is going to be a little weird, so I'm going to help you out with that one. The first person picks somebody. What's the probability that they pick somebody? 1. They're going to pick somebody, right? The whole thing is, do the other people pick the same person? That's the trick. So the first guy picks somebody. What's probably they pick somebody? 100% chance they're going to freaking pick somebody, right? And what's probably the second guy picks the same guy? 1 out of 5 chance. In fact, all the way down, right? All right, I'm going to get tired of doing that shit. How else can I write this? 1 times 1/5 to the 8. 8 guys pick the same guy as the first guy did. That's why one reason I love stats is because you can very often read in English what you just wrote down in math. 8 people pick the same guy out of 5 that the first guy did. Right? That's going to be a really small probability. That's why if 9 people identify the same person, I do them one at a time, they say, that guy. The next one, that guy. I'm like, that guy freaking did it, right? Because the probability he didn't do it is this. That's the probability that that's not the right person, right? And that's a really crazy small probability. You ever heard the story about the 4 guys who were on the way to school, and they said to the teacher, we were late for the midterm because one of the tires blew. And he says, all right, I'm going to ask each of you a question and want you to go to different rooms. So the first guy's in the first room, and the professor comes in and he says, tell me which tire blew. What's the probability that they all pick the same tire? It's the same kind of problem, isn't it? The first guy picks a tire, and then the other 3 have to pick the same tire. So if they all do pick the same tire, the professor's going to go, okay, I believe you then. That sounds good. If they don't, screw you guys. You're all failing, right? I don't know if you ever heard that. No? Okay.
The thing in this question that confused me was the part where they said all 9 victims, if the voice identification were made by random guesses.
And that's what this is. What's the probability that you would randomly pick a specific dude out of 5? 1/5.
Okay, so
Right? So a big distinction to make here is if they were just guessing, they didn't really know, and they were just guessing, then they're not going to pick the same guy probably, right? But if they all do pick the same guy, and I go, what does that mean about did they randomly guess? Well, this is the probability. If they all pick the same guy, this is the probability they did it randomly. So what's more likely? They actually just randomly picked the same guy, or that guy did it? Which one's more likely?
That guy did it.
That guy did it is more likely. There's a chance I'm wrong, but they are chances that I can live with being wrong. That's a really small chance of being wrong there, right?
So would that constitute reasonable doubt?
Yes, exactly. That's that exceeds the requirement for reasonable doubt. So, yeah, exactly. And that's why DNA evidence is admissible, because the reason it's such a small chance that it's wrong that it's accepted. Okay. Of course, you guys, I don't know if you guys realize this, but there's very small chance DNA is wrong. But the more cases that use it, the higher the chances that one of them is going to be wrong. If you think about that, right? But which way do you want to live with yourself? That's a hard question for society to answer. Okay. So we're going to get into section of chapter 5 today. And I've got a little handout that I want you guys to work on. I'm hoping that 5 goes relatively quickly. It's a little less vague. I think chapter 4, sometimes students don't like it because it seems a little vague. Yes?
The quiz is just all of chapter 4?
Yeah, the quiz is just on chapter 4, exactly. This, what we're getting into now, chapter 5 and 6, and I can't remember how far I went, but that's going to be on the next test. This quiz coming up on Tuesday is only chapter 4, only probability.
We didn't finish for
Chapter 4. Yeah.
We didn't finish chapter 4. We still have 4-6.
No, we don't. It's not in the main curriculum if you look at your homework sheet.
Yeah.
Okay.
You not include chapter 3, 4, something, right? 3, 4, the last one, right, for the quiz.
It doesn't include that one. 3, 4 will be on the next test.
Oh, okay.
But I want this quiz to only be probability. So let me ask you this. I'm going to try to show you why the math works. So what I'm about to do, you never have to do yourself directly. And then we'll do a problem and show you how to do it directly. But I'm going to try to show you why the math works. If I have a list of data like this, what is that? 3. And I ask you to calculate the average, what would you do?
Add it up, divide by
Yeah.
how many?
Exactly. Cool. Right? And since there's repeats here, can't be a little smart about how we add them up? If I want to figure the average, couldn't I do 3 4s plus 2 5s plus 4 6s
Sure.
plus 1 7 if I wanted to be silly like that, right? Isn't that okay?
Yes.
Of course. Cool. Right. So if I have some repeats, I can kind of group them together. Divided by.
How many?
10 in this case, right? Now, I could continue down this road and I get to the average. Anything else I do that is mathematically legal will get me to the same answer, of course, right? That's what we learned from algebra. You got to get to the same answer even if you go to it two different ways. So if I do this directly from this, what do we get? 5.3. What's the LDN? Is that 5.3? Yes, 5.3. Cool. All right, so you guys want to trust me. I like that. That's cool. Now, here's the other way to do this. And again, this is explaining why the math works. And this actually kind of goes back to that weighted average question from a while back. This really actually directly addresses that. Couldn't I say then that this is 3 tens times 4 plus 2 tens times 5? Now I'm really getting freaky here, right? But isn't that still legal? I don't have to divide at the end. I can divide each one in the middle, right? Math says, sure, man, what the hell? And what's 3 tenths? 0.3, so 30% of 4 plus 20% 5, 40% 6, 10% 7. Right? What does this 30% really tell me about 4? Go back to the original list.
Sweet.
Yeah. How much of the list is 4s? 30%. Right? And this is the whole idea of weighted average. The weight times the value plus the weight times the value. I don't know if you guys remember that one problem I gave you before. That's how we calculated it. What do we get here? We know it's supposed to be 5.3 if I did it in my head correctly. This will be 1.2 plus 1, 2.4, 0.7. Sure enough, that's 5.3. Of course it is. That's not the amazing part. Here's the cool part. What we're going to see the data in this chapter, or this section really, presented as, they're not going to give me a list, thank God. Because it could be like 88 4s and 111 5s. They're not going to give me this big-ass list. They're going to say, okay, I'm going to build up to this in a minute. I have some 4s, some 5s, some 6s, some 7s, right? What percentage of my data is a 4? And another way to look at it, what's the probability that I would get a 4 if I pick something from my data? 30%, because it's 30% 4s, right? 30% of my data is 4s. And that's exactly why that's the 30% right there. 5s,
2%.
20%, careful, 2 out of 10. 6s, 40%. And 7s, 10%. Now what, these better add up to be what? 100%, or 1 in this case, since they're decimals, or else I left somebody out. They have to add up to 1 or 100%. Thank God they do add up to 1. Now, can somebody tell me, and we've done this kind of thing before when we did standard deviation. You don't ever have to do standard deviation like this ever again, but there obviously will be other things we have to do like this. What would I put here to kind of match up with what I did here? What do I want this column to be? Where'd that 1.2 come from? Where'd that 2.4 come from? I love it. So what should the label of this column be? X times P of X. You multiply across, add down. So the sum of X times P of X is 5.3. Is that cool? There's my X times P of X's. That's what that column is. That's the X's times the P of X's. That's what that column is. When I add them together, so what symbol do we use for that? The sum. So the sum of all of these is 5.3. And what was that again? That was the average. So that's the formula for the mean. Okay. So real quick here, you guys figure out the average this way on a table. Do it for this table here. What should you check first before you do any work? What do you think you should check first to see if it's even valid? Yeah, these better add up to be 100. Or 1 in this case, and they do. One other little thing, they should all be between what two values?
0 and 1.
0 and 1. So those are the two checks to tell you it's a valid probability distribution. Probabilities add up to 1, and they're all between 0 and 1. So they both check out. Some of you guys might realize this is beautiful for your lists in your calculator. L1, L2. L3 would be L1 times L2. Know what you guys are getting for that? And when you add them all up, what do you get? 3.42. 3.42. And what would the average be just of the data directly? If I just had 1, 2, 3, 4, 5, what's the average? What's the average of 1, 2, 3, 4, 5?
1 and a 5.
What's the average? Not probability. If I had the numbers 1, 2, 3, 4, 5, what's the average? 3, because it's right in the middle, right? Or add them all up, divide by 5, right? Why is that average a little bigger? Why is that average bigger than it would have been if I just would have had one of each of these? What's the heaviest weighted thing in here? 3. What's the next heaviest weighted thing?
5.
Ah, yeah, see, right? So that 30% of 5s pulls the average up a little bit. You see that? So if I had 100 numbers, how many of them would be 1s? 7 of them, right? 7 out of 100. 13 would be 2s, 41 would be 3s, and that's why, again, they're not going to give us a big-ass list, thank God. They're just going to give us the percentage that are this, the percentage that are that. Makes it a lot easier to work with. Okay. So is everybody cool with that? You guys, that's not terrible math at all. That's pretty nice. The part's going to be just slightly freaky is the other number that I desperately want to have. And what other number besides average do I want? That'll standard deviation, right? Those are the two numbers. I don't care what the form the data takes on. I always want to figure out how to calculate those two things. So this is how I calculate the average. How the hell am I going to calculate the standard deviation? Well, I'll show you. And we'll sort of do it on the side here. The formula for standard deviation, or let's just say for the variance here. The formula for variance was this before, right? Cool. That's the formula for the variance. I want that same thing, but now I've got to take into account that the weights of each thing, right? So to do this, I would actually have to, so now I'd have to do this times the weights and then add those up. That would be the variance. What's kind of missing here that's in there? What's missing here that the first formula has?
And
Beautiful. But what's on the bottom of every probability? What's always at the bottom of a probability?
The number.
The total number of things, which is n. So you see how that has that built in? These are the same freaking equation. Are you guys with me a little bit? That equation sucks. I don't want to figure the mean and do the minus and then multiply by and square the damn. Oh, screw that. I don't want to do that, right? So thankfully, we're not going to do this either, all the way. But can you guys help me out? If I wanted to FOIL this thing out, what would that be?
X minus.
Minus mu x, right? You can get minus 2 mu x for the OI piece of FOIL. So minus 2 mu x plus mu squared. Then you could distribute this thing in there and all this kind of crap, right? Where you end up, we're not going to go through all that because this is not summation notation algebra class, right? This is probability. So at the end of all this business, you'd end up with x squared p of x. And you can see that when you get that, if you distribute that up here. This other part, though, all this other stuff, all that other stuff kind of reduces down to just the mean squared. It's awesome. That's what the variance is now. That's the formula that we're going to use. Sorry. So let me put that up over here for you guys. So variance used to be this. Oops. Now, the variance would be this. And if we work at this a little bit, we end up with that. That's the formula we're going to use. Now here's the cool thing related to what we have to do to get the mean anyway. To get the mean, I have to get this column here and add them up, right? What does that formula need from me? What do I have to add up for this Oops, over here. What do I have to add up for this formula? I have to have an x squared times p of x column, right? So you guys are cool. So remember, anytime we hit a new formula, you just cover that sum symbol, and that tells you, oh, I need a column of this. Well, I've already got a column of x p of x, don't I? How do I make it x squared times p of x? I don't just square it. That would be x squared p squared. That would suck, right? How many more x's do I need to make it x squared?
1x.
So I just multiply these two together. What's x times x p of x? Isn't that x squared p of x? And isn't that exactly what this dude says he wants?
Yeah, same thing.
Same thing. Cool. So this would be, if you want to call this L1, L2, L3, because you can kind of feel that we're going to go in that direction. Then L4 would be x squared p of x. That would be L1 times L3. So just doing it by hand for right now, what would I get here? I'd get 0.07, 0.52. You guys see what I'm doing? L1 times L3 to get x times x to make x squared. 3 times 1.23 is 3.69. 4 times 0.36, 1.44. 5 times 1.5 is something, 7.50. Then you add all those up and throw it into the formula. Because the formula needs the sum of these guys. So what's the sum of these guys? You just have to add those up. $13.22. So then the standard deviation would be, the variance would be, just throw it in now, right? So you guys, the variance, you just throw in 13. This whole thing is 13.22. And what was the mean? 3.42. So for you guys over here, throw in there 13.22 minus 3.42 squared. That's the variance. And how do you get the standard deviation? Take the square root, 11, right? So let me show you real quick. That same problem I think I'll do in here. Because the handout I have, on one side it has a worked out example, on the other side it has a blank example that I'm going to want you guys to work on. Okay, that's nice. So if I want to do this in the calculator, let me do this way. I can clear all my lists. Number 4. Oops, got there. If I clear lists, L1, L2, L3, I want them all clear.